All right. Now, if this is your first BioSTEAM workshop, you might not even understand what is behind BioSTEAM. So I like to give you a bit of a preview of the structure of the software. BioSTEAM includes five core components, which enables streamlined TEA, techno-economic analysis, and LCA, life cycle assessment. So the first component here is in blue, the process equipment, which allows for mass and energy balances, sizing, and costing of unit operations. BioSTEAM is written in Python, which is an object oriented programming language. So a lot of the features are coded in as objects. Every unit operation has the same framework for unit objects, and that allows you to add heating and cooling utilities, power utilities, and define how you get your output streams from your input streams and how you want to size and cost them. We also have the thermodynamic engine. The stream object is the main interface for you to, one, collect the flow rates, temperature, and pressure between unit operations and perform phase equilibrium and estimate mixture properties. And we use the thermal library in Python for thermodynamic calculations. The thermal library has over 20,000 chemicals in the database, and we simply gather all that data and formulate thermodynamic property packages in BioSTEAM. We also have automation tools for uncertainty, sensitivity, and optimization all through this model object. So the model object contains a system object, which is uses to simulate across a landscape of different scenarios for uncertainty analysis, for example. And we have simulation tools for process modeling, TEA and LCA. That's mainly just the system object. It takes care of figuring out which order to run your unit operations, how to solve recycle loops, and take care of converging a process. And lastly, we have the Bioindustrial Park, which has all the community-led biorefinery models. Anyone and everyone is welcome to contribute to the Bioindustrial Park. We don't have such a high standard compared to BioSTEAM in terms of the contributions. So before publishing your paper or after you publish your paper, then we'd be happy to accept your biorefinery or process that you want to contribute. But we do recommend having tests to make sure that in the long run, your biorefinery will still work with any BioSteam version. On GitHub, once you create an account, you can click on this star here after going to the BioSteam GitHub repository in order to tell others that this is a very good repository and they should give it a shot, right? Now let's go on a tour of the BioSteam documentation. So if you're a new user, mainly you want to start here at the user guide, right? But if you haven't installed BioSteam yet, there's some detailed instructions down here. So just scroll down and you'll find how to install BioSteam. I recommend first installing the Anaconda distribution for Python. And BioSteam works on Python 3.13 or above. So after you get the Anaconda distribution for Python 3.13, you can pip install BioSteam. Or if you're good with GitHub, you can actually clone directly the repository on GitHub. Then, if you want to get the diagrams working, you're going to need to run one additional line, which is conda install Python GraphViz. And that should take care of getting GraphViz logged into Python. And GraphViz is another software that BioSteam uses to generate diagrams, but it's not directly in Python, if that makes sense. And there's also some common issues that people usually get when installing BioSteam. For example, you might need to install C++ build tools here. It happens for a few people using Windows. Yeah, and we have a number of different scientific papers that might be interesting for you to read, but this is more to show off more than anything. Now, for the user guide, you want to start in the beginner's guide. It tells you everything about stream objects, thermodynamics, how to create a unit operation, how to connect and form a system, as well as how to manage your preferences and, for example, whether you want dark mode or light mode diagrams, or what units of measure do you want to see your results in. Process development is basically diving deeper into features for modeling a process. So this might include creating your own unit operation with your own mass and energy balance algorithms, could be defining process specifications whereby maybe you want to vary the titer of your fermentation by adjusting the amount of sugar coming in or adjusting the amount of water being vaporized by a multi-effect evaporator. And that example is actually in there in the process specifications tutorial. And we got more detailed TEA and LCA tutorials too. Now, thermodynamics, there's a whole lot to that, right? Especially when it comes to chemical engineering and process simulation. So I try to be as detailed as possible. And I also included here a thermodynamic fundamentals tutorial, which is more educational rather than focusing too much on BioSTEAM. Automation features for the model object for performing uncertainty, sensitivity, comparing different technologies under uncertainty, and even for operational flexibility when you try to operate at different modes, different feedstocks, different bioproducts throughout the year. That's also possible to model in BioSteam. Many people, when they go to perform these analysis, simply control copy the entire tutorial and just adjust things here and there so that it fits their own case study. Now, for advanced unit operations, this includes very rigorously modeled unit operations in BioSteam that require many input parameters and many design decisions. And it has a lot of details in the equations and underlying equations and variables within the unit operation. So we're going to be focusing on the bioreactor design in today's workshop. And we'll have a look at this case study for aerated fermentation. Cool. So in this tutorial, we'll go over anaerobic fermentation, aerated fermentation, mainly focusing on microbial oil production from sugar. For anaerobic, just be using the conventional corn ethanol production. And for the gas-fed fermentation, which consumes carbon dioxide and hydrogen, we'll be looking at acetic acid production from blast furnace steel-making flue gas. And this is actually a deployed process by Lancetech. I believe they have one in South Africa and another one in Europe. I might be wrong, but I know that they've already deployed this technology, which is pretty cool. So overall, the goals of the tutorial is to understand the equations behind the simulation and how does BioSteam design the bioreactor. Then we'll be able to apply this BioSteam unit operations to model the fermentation processes once we've understand the governing equations. And more broadly, we'll understand the difference in the modeling complexity and economic impact of between anaerobic, aerobic, and gas-fed fermentations. All right. Now, for a bioreactor, we have 5 governing equations. We have conservation of mass, and here I've wrote it in terms of the feeds coming in, right, and the products. So out minus in equals generation. Your phase equilibrium, so your fugacity in the gas and the liquid need to be the same. So that's what allows a certain fraction of ethanol and humidity to leave to the vapor phase in fermentation, for example. Or if you're looking at aerobic fermentation, then you have this equilibrium between oxygen in the gas phase and the liquid phase that helps determine also your mass transfer. Conservation of energy, to understand your cooling duty, is just the enthalpy coming out minus the enthalpy coming in is equal to how much you need to cool. And your mass transfer, we need to account for mass transfer rates within the liquid to make sure that you're satisfying your oxygen demand. And your heat transfer, This one is a little bit more preliminary because many times the costing algorithms make some heuristic assumptions on what's the necessary heat transfer area and such. So the heat transfer is a little bit easier for us to model for preliminary TEA and LCA. All right. Any questions until now before I go into an anaerobic bioreactor design? All right, let's go into it. Here, we're going to have a look at conventional dry grind process for corn ethanol production. So the corn is liquefied and saccharified to create a slurry. And so the slurry is basically sugar and water. And we can ferment that to produce ethanol and carbon dioxide. And we'll be making these assumptions over here on the flow rate, glucose concentration, ethanol yield, and temperature. And we've listed them out by code here. So the mass balance is pretty straightforward. Whatever comes out is equal to whatever comes in plus whatever gets created. And here we're specifying the mass balance in terms of a theoretic ethanol yield for this equation. So you have the amount of glucose coming in times your stoichiometric coefficient times the theoretic yield, and that will give you your flow rate coming out. Now, for the mass balance, we also need to take into account vapor liquid equilibrium. And going into a detailed calculation for that is not trivial at all. So we'll just be using BioSTEAM's vapor liquid equilibrium capabilities to model that. So here we are. The first thing we do in BioSTEAM is define the chemicals. Now, BioSTEAM has a number of biorefinery specific chemicals that are not necessarily official chemicals, right? Like yeast, but it helps standardize the modeling of these components within a biorefinery by using the BioSTEAM database. So here we're defining water, ethanol, glucose, carbon dioxide, and yeast, which is not a normal chemical, into the set of chemicals we're working with. Then we can create a stream. Here we're setting the fraction of water, glucose, and the total flow as defined above in the first cell. And here we're creating our product streams. We have our broth, our vent, and our broth is what comes out of the fermentation. And our product is a combination of both. So this is actually a multi-stream, which is, you can think about it like a collection of multiple streams. And you'll see how to use it a little more as we dive deeper. And here we're defining our reaction using BioSTEAM's reaction object. So we define a string of the reactions using the names that we define, whereby we define the chemicals and the yield. Here we're defining a growth reaction as well. And we're just assuming the mass balance is conserved. We're not interested in the atomic balance. This is just for preliminary analysis, right? If we were concerned with the atomic balance, we would need to include more nutrients like a nitrogen source, a phosphorus source in order to balance out the atomic weight of yeast. So here we created what's called a reaction system, which is multiple reactions in series. And here we're going to react. First, we're going to get the flow rates from the feed to the broth. So we're copying everything from the feed to the broth. Then we're reacting the broth through the reaction object. Then we're performing the vapor liquid equilibrium through this method here in BioSTEAM between the vent and the broth. And here we have our results. We have our feed, our reaction system that we defined previously, and our product, which contains the vent and the effluent. So in BioSTEAM, you wouldn't actually go through all this trouble to model the fermentation process. Instead, what we would actually do is, I'm going to skip a little bit here, is simply use BioSTEAM's unit operation and define the feed and other input parameters. Now, I'm just showing you what happens within the unit operation to help you understand how BioSTEAM works. And we'll get to all these other details very soon. In any case, the results that we got from the mass and energy balance is the exact same results that we get here from this unit operation. So when we define a unit operation, we specify the inlet, the outlet names or actual streams, and other input parameters. We simulate, and then we can get diagrams and look at the results. So let me go back up here. We talked about the mass balance here. Now we're going to move into the energy balance. And the energy balance is super simple. All that we really need to know is the cooling duty, and that's just the enthalpy coming out. And we can access the enthalpy of a stream by using .H as the enthalpy. And the enthalpy of formation is with HF. So enthalpy coming out minus enthalpy coming in is your cooling duty. And that gets accounted for in the unit operation too. And finally here with bioreactor sizing, there's a lot of heuristic design specifications that we can make, such as what is the length to diameter ratio, what is the maximum reactor volume. Around 1,000 meters cubed is a good assumption for corn ethanol. What is the working volume? Reaction times, cleanup, loading, and these are all good heuristics that you might need to change if you're producing a different product. For example, the reaction time, that's going to depend on your product. And wow, I need to remove this additional line here. It's repeated. Okay, so these are the equations that we use to solve for all these parameters. And they're very straightforward. It's just a little bit of math, but we go ahead and solve those equations over here just to show you the results that we would get in BioSTEAM. And these are the exact equations we used in the unit operation. And you can go back and double check. Now for heat exchange, to understand how you need to size a jacketed vessel or external heat exchanger loop, that can get a little complicated because it depends on how fast are you steering, right? What is that overall heat transfer coefficient in order to size it correctly? But what actually happens is, regardless of whatever your heat transfer coefficient is, you can always just flow in more chilled water or whatever your cooling agent is in order to meet that demand given a specific area. And for a jacketed vessel, the typical area is the entire surface of the vessel. So, given a constant area, all what we really need to find is the flow rate of your cooling utility. Now, for preliminary economic analysis, the flow rate doesn't matter. It's the duty that matters. That's what determines the cost that you incur for your cooling, especially your chilled water. So ultimately, all those additional design variables or all those additional variables that you would get to rigorously design a bioreactor doesn't really matter for economic analysis. And here we can get our chill water flow rate with some additional assumptions and specifications. And please feel free to read this a little more in detail. I know first time hearing this, you might be a little confused. Like, what? We don't need to know everything about a bioreactor? The truth is, you don't. All right. Now, for a standard anaerobic bioreactor model, here we're using the BioSTEAM unit operation, and we can see that we get the exact same results in terms of the flow rates. And when we do dot show, we can look at the uh, inlets and outlets. When we do diagram, we can look at the bioreactor. And here we're having a look at the bioreactor results. And it's a lot. And many of these things you can change as input parameters to the unit operation, including the vessel material. Okay, any questions until there before we move into anaerobic? Oh,
So you're
sorry, let's yes, go
yeah,
ahead.
yeah, this is Arvind. I had one I guess a high level question.
Hmm.
If I have a new feedstock and I don't have an established process to perform valorization on it, what can BioSteam do to help me? Starting from scratch. I may have a research paper from somewhere saying, use this bio waste feedstock, use these
Hmm.
solvents and things. To some extent, I may have some information, but what can BioSteam help me do to create a process?
Yeah, yeah. Well, I think there's several resources that you can use. Um, the first thing is, I guess the most important thing is for you to read the full paper and understand all the underlying assumptions, right? Only
Mhm.
then can you
Mhm.
begin to build the process and to build the process well. So once you understand what thermodynamics is necessary, what unit operations are needed, then you can try to find if BioSteam supports those modeling capabilities. So if, for example, you're producing 3-hydroxypropionic acid or acetic acid, ethanol, and a number of different bioproducts, actually, or your feedstock is some of the same feedstocks that we've modeled before, then you can go to the bioindustrial park and control copy or import some of those processes that are already there for separation, pretreatment, and so on. Let me just show you something here for biorefineries. Here we have some documentation. It's not too detailed for some of the main biorefinery models from the bioindustrial park. So here for cellulosic, for example, you can create a full biorefinery. But for systems, there's a number of different systems that you can create specifically related to cellulosic processing, like hot water pretreatment, dilute acid pretreatment, ammonia fiber expansion, alkaline pretreatment, or the full cellulosic ethanol production system. So we try to break it out into different blocks, different sub processes, so that it's easier for you to drag and drop. I should mention some of these functions are used throughout many different biorefineries. So if you're, for example, hot water pretreatment is used for corn stover, for sugarcane and miscanthus, for many different biorefinery processes. Yeah, that's one of the resources that we have, and then there's the whole tutorial over here that can help you paste things together.
Okay, thank
I
you.
hope that helps answer your question. Thanks a lot for it. All right. Now, we also have, in addition to the standard anaerobic bioreactor, we have an enroll bioreactor model. This is only for anaerobic cellulosic ethanol production, but people like to use it for corn ethanol as well. And if you look at some of the results that we get here, the Enroll model actually shows lower capital, but it's still within the same order of magnitude. So it's normal for equipment costs to vary significantly between different models, right? Since capital cost is one of the most uncertain things out there, and correlations typically have between -30 to +30% uncertainty. So the standard method is based on the correlations for average capital cost paid in industry, while that the Enroll model is based on a preliminary vendor quotes. Now, standard methods are often over-designed and would lead to greater cost, while vendor quotes tend to be a little more accurate, but are optimistic, and many times you can find unforeseen expenses during construction. So if you're looking to be conservative, you would go with maybe the standard model. If you're specifically working on cellulosic ethanol, you might go with the Enroll model, of course. All right. So those are two anaerobic bioreactor models. Let's move into the aerated bioreactor. Now, I did say this was just 1 hour, but I'm gonna extend the tutorial to an hour and 15 minutes more or less, just to make sure we hit everything. So for the microbial oil aerated bioreactor, here we have a full example. Now, there's many different reactions going on here. We have production, we have growth, and we have respiration. And respiration is necessary in order to drive production. And here we have a list of assumptions that we're making for microbial oil production. And we can translate these specific yields that are in weight percent, not theoretical, into theoretical yields as such. Don't worry too much about the math. The main goal here is to show you how we can define this full reaction system where you have production and growth paired together. And after that comes respiration. And this is actually a standard way to model aerated bioreactor reactions. And here we have our reaction system. Now we're going to move into the mass balance calculation. And here we've specified the titer and the amount of glucose coming in. So that'll tell us the volume of water that we need. And we need to solve for how much dilution water do we actually need to achieve that titer. And we can do that numerically. So here we have our feed coming in. We have air coming in. Now we won't be too concerned about the air just yet. We're just going to assume that the amount of oxygen that we require is the stoichiometric amount of oxygen. So we're not accounting for mass transfer just yet. All right, so we defined all our streams. And here's where we're doing all the math. So we have our stream coming in with a given amount of water. Then we ferment that stream. So we're copying the feed into the effluent, fermenting it. Then we're adjusting the amount of air coming in to meet that required stoichiometric amount. Then we redo the calculation again so that the amount of oxygen is accounting for. In other words, first we're doing the calculation without any oxygen. Then we find out how much oxygen is required and we add that in. And finally, we can react with the appropriate amount of oxygen, and there we get our true product. Finally, we perform vapor liquid equilibrium. We compute the titer, and that gives us the titer as a function of the amount of water coming in. And then we can solve it numerically. Now, again, this is not what you would do to solve an aerobic bioreactor in BioSTEAM. Rather, this is letting you know about the underlying equations that happen and algorithms that happen within the unit operation. Now we can perform the same calculations for bioreactor sizing, and that gives us the reactor volume, the height, and so on, given the set of specifications. Now, there's one more equation here that we're not accounting for, and that's the mass transfer. In an aerobic bioreactor that is very well mixed, then the mass transfer within the liquid is actually very fast. The mass transfer within the gas bubble is also super fast since the gas bubble is so small and is within a gas, not a liquid. Mass transfer is much faster in a gas. So the limiting step is at that boundary layer between the gas bubble and the liquid. So we have at the interface, we have some vapor liquid equilibrium between the oxygen and the liquid. And then we have a small boundary layer here where we have a huge change in the concentration. And we can model that boundary layer as what we call a mass transfer coefficient times the driving force. So there's a lot of details in the mass transfer, and we can estimate the oxygen transfer rate based on this mass transfer equation. Now, the mass transfer coefficient is going to depend on how you operate your aerated bioreactor. And this is a very simple correlation here that depends on the power and your agitation and the velocity of your gas bubble. So if the gas is flowing very fast, then you have faster mass transfer because it decreases the size of your boundary layer. I don't want to get too much into chemical engineering, but I just want to show you that BioSTEAM includes rigorous modeling for mass transfer, pressure accounting, heating duty, and vapor liquid equilibrium, in addition to, of course, the reactions. So here we're solving for the amount, the flow rate required at a specific agitation power in order to meet that mass transfer uptake, right? So our oxygen uptake rate must be equal to our oxygen transfer rate. Now, I won't go into detail here because it's too much detail, but rather this is what happens behind the scenes for the aerated bioreactor. And these are the results that we get for the vent and the broth, and these are our feeds that we require to meet the specific titer. So we achieve the correct titer. Heat transfer is very straightforward. Finally, here we're modeling our aerated bioreactor. So we include the reactions that we detailed previously, additional heuristics for the volume fraction within the bioreactor. What's our maximum volume, our reaction times, our loading time, length to diameter, and then the methods that we're using to solve for the mass transfer coefficient. What type of heat exchanger? We could have also done an external heat exchanger, and so on. And this is what the aerated bioreactor kind of looks like. We have the compressor, the air cooler, and the bioreactor itself with our mass and energy balance and our full detailed outputs. All right. Any questions on the aerobic bioreactor model?
I just have one question. I see
Mm-hmm.
the copy like stream you usually do for example, broth stream. I would like to
Mm-hmm.
know what exactly you do this, or what is the
Yes.
advantage, and when to do it and when not to do it.
Yes. Yes. So all that copy like does is it copies the flows and thermodynamic conditions of your other stream so that they're virtually the same streams after you run copy like. Let me go to a specific. Here we go. Mix from copy like. So, what's actually the reason we're doing this is because we don't want to change the feed. The input to a unit operation must always remain constant. Otherwise, we'd be introducing a bug into BioSteam where, you know, you're changing your inputs for a unit operation. So that's why we like to work on the product. So after we've copied the flows from your feed to your product, then you can react your product as done here. And that will give you, you know, the amount of ethanol coming out or, you know, microbial oil in your product stream. Does that make sense?
Mm, a little bit.
A little bit.
So, but
Okay.
because here in this process, the inputs are the feed, and then you have two outputs, right? There's the broth
That's right.
and the vent. The broth is
Mm-hmm.
like the liquid feed, the feed is liquid, and the broth too. Because I have some, I made
Yes.
to say the truth, I've made some simulations, and sometimes they have some problems because it
Mm-hmm.
gets an error about the phase of the stream, and sometimes
Okay.
they say that it's a liquid or solid and so on, and so that's why I'm asking too.
Yes. Yes. Yeah, you want to keep the broth as a liquid. Yeah, and if you get any errors in unit operations, feel free to post the error on GitHub issues. in the BioSTEAM
Okay.
repo or the Bioindustrial Park
Okay.
repo.
Mm-hmm.
Mm-hmm. Yep, yep. All right. Cool. Any more questions? We have time for one more. Okay. Well, to finish up here with the bioreactor, it also includes a internal unit operation called the compressor. And if you want to look at detailed results for the compressor, it works just like any other unit operation. It's just uh, embedded in the bioreactor. And you can have a look at the flow rates of the compressor and the results. All right. Now for the gas-fed acetic acid bioreactor, is the same equations. So I'm not going to go over all the equations again. Rather, now we have hydrogen and carbon dioxide being fed into the bioreactor, and we have mass transfer relationships for both chemicals. Now, we need to use the gas-fed bioreactor unit operation to solve it, to solve this multiple substrates being transferred to the liquid. So here we have our media, hydrogen, our flue gas. Then here we have the reactions that take place to convert the flue gas and hydrogen into acetic acid. And finally here we have our gas-fed bioreactor with our three inputs, the media and the additional gas phases. The first one is always the media. The other ones are additional feeds. We have a set of assumptions regarding how do we size the bioreactor. Now, for this bioreactor, since we have the substrate is very important, right? We don't want to lose hydrogen in the vent. We want to maximize that mass transfer, maximize the consumption. We need a very high length to diameter. And this is a more common length to diameter for this type of fermentation process. If we were doing aerobic, it would be more around 3. In any case, we also need to define what are the substrates being transferred. And we're designing this as a bubble column. So a bubble column does not include agitation. Rather, the bubbles just flow up and they help steer the bioreactor. Here we have a look at all the results. For those specific flow rates of hydrogen gas and flue gas, we're able to generate this amount of product. So our product is about, I'm not exactly sure what titer is that. So it's 4%. So that's about 40 grams per liter in titer for acetic acid. And here you'll notice how we weren't able to consume all the carbon dioxide and a little bit of hydrogen is left over in the vent. Okay, any questions on the gas-fed bioreactor?
I think there is a question from the previous in the chat from the
Oh, okay.
previous.
Oh, wait, there's multiple. Oh, okay. We already answered Arvin's question here. Now with Sarvada's question, thank you. How is the yeast stream tunable to include various types of microorganisms? Mm-hmm. So if you want to include other types of microorganisms with their own formula, then you will want to create your own chemical with said formula. And there's many different ways to create a chemical, or sorry, there's a standard way to create new chemicals, but you don't need to necessarily define all the different properties. You can just default them. So if you know what is the density and the heat capacity, the formula for your uh, microorganism, then you can add all those details. But otherwise, you can just specify the formula and let BioSTEAM default all the other parameters. Now here in thermodynamic engine, it gives you more details. Wait, maybe not there. property package right here. So here in property package, it gives you some details on how to create your own chemical. So you want to specify the phase. If you have the density, you can specify that. You want to default other chemical properties like viscosity, because it might not be too important for your simulation. And you want to give it the formula. So I think around here we have dry yeast, and here we're specifying it as such, and we don't really care about the formula since we're just modeling it by mass. We're just saying a fraction of glucose turns to dry yeast. We don't care about the nutrients at this level. Thank you for the question, Sarvata. Now, Barath has another question. Can BioSTEAM be used to model oil and gas processes or other ones other than bio-based? Yes, it can. It's getting more usable for those applications. So, for example, recently we introduced Gibbs equilibrium reactor, which solves for an equilibrium reactor that minimizes the Gibbs phase energy. This is very common in oil and gas processes. The distillation methods that we have in BioSTEAM are super rigorous as well. It's not just shortcut columns that make assumptions on your optimal design, but rather you can specify the stages, reflux, feed stage, and many other variables for the distillation column, and it'll solve all the thousands of equations and variables rigorously. And we have a number of different methods that are used. And if you're curious to know more about that, you can check out the distillation modeling and design tutorial that goes over it. But we use the most robust method out there, and is the inside out, which is what Aspen uses for RadFrac. And it's complicated. It uses surrogate modeling to solve the method. And here we're looking at many different methods to solve the column, and it achieves like 10 to the minus 60% error in the simulation variable. So it's quite rigorous. Okay, I hope I answered that, and hopefully not too deeply. Now let's move into aerated fermentation process case study for oleochemical production. So here we're going to look at a full microbial oil production process. And this is the from feedstock to fermentation flow sheet. We're not including downstream separations just yet. And now there's more details on the assumptions for mass transfer and so on, but we can skip all that since we talked about that already. And in this code over here, we specify our chemicals that we're using, all the reactions. Then we create our aerated bioreactor, just like we did in our previous tutorial. And here we're setting additional parameters like the titer, productivity, and the lipid yield. And this is just a place that we can add the data, and then that data becomes useful for solving the specification. So we're adding here as a process specification for the aerated bioreactor to update the reaction time and the yield before it simulates. So anytime the aerated bioreactor simulates, it updates the reaction time and the yield. And this is what we created with the aerated bioreactor. Now here, we're adding the additional unit operations. We're creating our feedstock, our multi-effect evaporator to achieve a high efficiency, thermal efficiency for the evaporation of water. Here we're adding a specification to the evaporator to adjust the amount evaporated in order to meet a given titer. You can just control copy this and control paste it if you need this kind of specification for your work. But just to summarize, what we're doing here is what we do is we adjust the amount of water around this code here. Then we run all the unit operations until the aerated bioreactor. We could have done E1.simulate and then, I don't know, mixer.simulate and then AB1.simulate, or we could use this code line over here, and then we're getting the error. So this is a fancy feature in BioSTEAM to solve for this variable, the vapor fraction, within these bounds for these given tolerances, such that the error in our target titer and our actual titer is 0. Okay, so after that, we're going to use a function here to create a system, to create the lipid extraction system. So this is a predefined system for extracting lipids from a fermentation broth, and that is such that the oils within the cells, right? So these are very fat cells, the oil is not outside for this specific system. Then finally here we're creating our full system, and the way we're doing this in this case is we're just giving BioSTEAM all the unit operations and letting BioSTEAM decide how to run the units, so in which order and how to solve recycle loops and so on. All right, and this is the full system that we created. So it includes not just the aerated bioreactor and the multi-effect evaporator, but also downstream separations, including the drying, conveying, removal of any water in our microbial oil product and washing, and the production of wastewater. Okay, so yep, here we're looking at some more results for the aerated bioreactor. And finally here, we're layering on TEA. So we're using an existing TEA framework called Create Cellulosic Ethanol TEA. Although it's been used for ethanol, it can also be used for other processes. It doesn't have any ethanol specific assumptions. Rather, it just comes from a specific ethanol model by NREL. So here we create the TEA object, and then using the TEA object, we can solve for the price for the liquid product stream. And this is the minimum selling price. So it's doing cash flow analysis. And finally here, this might be, I'm not sure if anyone here is doing optimization. This might be useful for you if you ever want to conduct rigorous optimization of your entire process. So although you could do it by yourself using SciPy or any other Python package, making your objective function that simulates your entire process, BioSTEAM already includes features to help automate that process. So here we can do this through the model object. You can pass your system to the model, define different parameters. So this is the pressure parameter of your aerobic bioreactor, the amount of power you're using for agitation, and the length to diameter ratio with the following bounds. You're defining your output indicator, in this case, the minimum selling price. And here we're just printing out, without any optimization, what is our minimum selling price and under what assumptions. Then after optimizing, we can get our new results. And it turns out that optimizing the aerated bioreactor can improve the economics, but not by too much. And this is because the heuristic design decisions that we gave it are actually pretty close to the optimal already. That's why heuristics can be very powerful. And here we're doing another analysis where we're varying the titer, rate, and yield and understanding what is its impact on the minimum selling price. So this can tell you, oh, at this titer, I need around this much productivity and yield to reach a minimum selling price of 1.3. And maybe 1.3 is your market price that you sell it at. So this can help you define goals and targets for your fermentation technology or whatever other technology you're working on. Okay, with that, I'll open the floor to questions. I've covered everything I wanted to cover. here. I can't see any of y'all right now. And I'm trying to find how can I see everyone. Let's see. Okay, I found it. Any questions, guys? I'm happy to talk about anything. Like if you're working on an entirely different process, I'm happy to answer questions on that. Um, yeah.
We have another question in the chat.
Oh, in the chat. Okay. Mm-hmm. Downstream separation is their code for fixed bed adsorption column in BioSTEAM. Uh, Tutorial code for graphics that can be visually used for biorefineries to compare. Okay, now these are great questions. Awesome. So for your first question on downstream separation with an adsorption column, here we have a tutorial on the adsorption column. It details the mass transfer equations being used, and specifically this is for adsorption of inks within a solvent for waste plastic dissolution. But you just need to change the parameters and it can be used for any process, right? So in this first one here, we're fitting data. This is more explanation on how the bed is sized for the adsorption column. Here we simulate the adsorption column and get all the results. And here we have the profile of the adsorption column through the length of the bed. So
Hi, Yuval.
through the
Can you
length of the
hear
bed and
me?
across time. Yes. Yes,
Hi,
I can hear
Yuval. Can
you.
you hear me? Yeah. So,
Yes.
we, I work with Emma Brace. We are working on xylitol biorefinery, and
Sure.
we are actually using this code as one of our unit operations. But the
Mm-hmm.
biggest difference between this is that the carbon, like the absorbent that is actually
Yeah.
absorbing the ink, it kind of flows with the thing. So it's not like a fixed bed, it's like a moving thing.
Oh,
So we have been having a lot, like we are still troubleshooting how to like change it to a fixed bed column because we are running into some issues with the breakthrough of the column. So that's the only reason I was curious if you already
okay.
have a
Interesting.
project that has used it
So,
already, because our adsorbent is expensive, so we
yes,
cannot use it with our adsorption chemical.
yes, yes. So for the actual unit operation, are you looking to have a fixed bed? Like industrially, if you were to implement it, would you have a fixed bed or um
Yeah, I
a
we are.
moving bed
It's not a
or
moving
just a
bed. It's gonna be a
just
fixed bed where
okay.
it'll. We were rather thinking that we would have like two columns staggered so that one can be down while the other is being changed or something. But we are looking for a fixed bed, not a moving bed.
Okay, perfect. So this unit operation fits you perfectly. And what you need to get is just the data. And you can get that data not necessarily using a fixed bed experiment, right? In fact, we don't use fixed bed experiments to collect this data. So, so, so,
Okay.
so, what you need is two types of experiments. The
Mm-hmm.
first one is where you vary the uh, concentration of
Okay.
either your activated carbon or your um, adsorbent, right, your solute,
Mm-hmm.
and look at the equilibrium constant, right? That's
Okay.
number one. Number two is you put a very small amount of carbon, very small, and wait,
So the thing is, we are not using carbon. It's a proprietary, expensive
Yes. So you
absorption
use
thing.
whatever adsorbent you need.
Hmm.
But this next experiment is for estimating the mass transfer coefficient
Okay,
because
okay,
those are the two sets of data that you need,
okay, okay,
right? So if you can get those two experiments,
okay.
right here, um,
So it's
this
mass
is the
transfer coefficient, and what's the other component that you mentioned?
so for your isotherm. So you're gonna
Okay,
need an equilibrium constant for your isotherm.
okay,
And it might not just be one variable, it might be several, but all you need
sure,
is the data. So
sure.
here we have two sets of experimental data. Here you have your isotherm data, and here you have your concentration across time of your
Okay,
solute. So you put a
okay,
very small amount of carbon with a large amount of solute, you let it
sure.
run, and slowly that solute is going to be collected in the
Right.
carbon.
Mm-hmm.
Yeah.
Okay.
Okay.
Yeah,
Yep.
thanks.
I hope that was helpful.
Yep.
Free consulting. Hey.
How about my second question? Do you have any tutorials
Oh,
already on the website?
tutorials for, let me see. Can you repeat your question?
So basically, something similar to that you just showed a few minutes ago with regards to MSP. Do you have that thing with like the graphics that you showed when you do like sensitivity analysis, or once you optimize it, how that changes? Just getting
Yes.
those
Yeah.
graphs visually. I'm not a coder, not an expert in
Yeah.
Python, so it's always helpful to have some tutorial graphics that I
Yeah.
could just
I
bounce off of.
recommend I recommend three things. First, starting off with maybe ChatGPT.
Okay.
Give well actually I take that back. I take that back. First start off by looking at here in the automation features in BioSteam because we use many functions already in BioSteam for plotting, such as this one here. Plot KDE, kernel density. I forgot what's the last
Okay.
acronym for. Uh, for sensitivity analysis, right?
Mm-hmm.
For box plots, for
Mm-hmm.
example. Here we have a more box plots that might be useful for you. And then in the what's it called? Not bioproduct separation. The last here we go. This heat
Yeah,
map
something
or
similar
surface
to
plot,
this. Yeah.
right? You can copy this to, generate your data even that you require
Mm-hmm.
and plot your metric. So that's mainly what BioSteam features in terms of plotting these analyses. Then I recommend using ChatGPT if you're looking to make different kinds of plots. I'm happy to take one more question. Oh, what? Oh, I would like to ask you about the possibility to combine custom process unit models previously fitted with the predefined ones in BioSteam. Yeah, there's many ways to combine, right? What you want to do is look at first this inheriting from unit tutorial, right? And that'll tell you the layout that unit operations use to define mass and energy balances, design, and costing. So you can inherit from an existing unit operation in BioSteam and override the mass and energy balance if you want, override the design, or override the costing. Everything is possible. And you can specify however you want to run your unit operation within the run function. So if you have some sort of surrogate model, machine learning model that can predict output compositions of your streams, or maybe a kinetic model that runs the where you can just ultimately get the final product flow rates given your feed, then you can put that in there. But all you really need is to get those output flow streams conditions. Does that make sense? Okay, great. Which kinetic model does BioSteam commonly use for fermentation sources such as microbial oil production? That's a good question. That's a good question. So we do not have a kinetic model for any other fermentation other than ethanol. And by default, the ethanol kinetic model is not used. So what we do is we specify the productivity, titer, and yield. And we can understand what impact on the economics can these variables have. But it's very easy just to add those kinetic models if you need to in BioSteam, just by subclassing from the but one of two ways. One is subclassing from the bioreactor and specifying the outputs given the inputs and whatever conditions you have. Maybe it's the fermentation time by using your kinetic model. So you would just replace whatever the code in the run function. Or you can add a specification. So just like we did in the aerated fermentation process around here, we added a specification to adjust the product yield and the residence time. You can run your kinetic model given your feed concentrations and whatever residence time you have in order to specify your yield. And like that, you'll have solved your entire fermentation process. All right. Cool. Well, if there's no further questions, I want to thank everyone for attending this workshop and just for finding an interest in BioSteam and for supporting it. If you can, please create a GitHub account and star the BioSteam package. And if you have any future questions, just let me know. I'm happy to answer. Thank you.